Hi, everyone. My name is Alan. Today, I'm going to present our work called HyperRecon, Regularization-Agnostic CS-MRI Reconstruction with Hypernetworks. The problem that we're addressing in this work is that of hyperparameters, and hyperparameters are, of course, ubiquitous in deep learning systems, whether that's regularization weights, network architecture, learning rates. There's a whole multitude of things that are considered hyperparameters, and these hyperparameters are very expensive to tune, and they must be set before training, and they cannot be changed during training or at test time. So you need to do very expensive procedures like cross-validation in order to tune the hyperparameters. A body of work that's trying to address this problem is called Hypernetworks. Hypernetworks generate the weights of the main network, which performs some task. So the main task would be like classification or reconstruction or segmentation, for example. And it was originally proposed in this paper, but since then it's been used for a multitude of different things. Specifically in this work, we were influenced by this previous work called stochastic hyperparameter optimization through Hypernetworks. And basically they were able to show that a hypernetwork can learn the same kind of optimized loss values across the validation loss for different values of the hyperparameter. So instead of having to train multiple different models that are represented by each of these X's, which are each a single model, they can learn a single hypernetwork, which is able to learn that curve. And that way you can do very fast hyperparameter tuning, right? And so this is basically their idea. So for hyperparameter tuning, you can basically view it as a bi-level optimization. So we have an inner train loss that we're trying to minimize, and then there's an outer train loss with an outer validation loss over the validation set, where we're tuning the hyperparameters, which in this case are alpha. So the authors proposed to learn the function theta star as a function of alpha, and this theta star minimizes the training loss for that value of alpha. And so the way that we learn this function is by using a hypernetwork, which generates the weights of the main network. And so the loss that we train is this, which is basically finding the weights of the hypernetwork phi, which minimize the training loss across a probability distribution of the hyperparameters P of alpha. So during training, we basically sample from these alphas randomly, and as well as minimizing this loss against the input from the main network. And so at the end, we have this theta star of alpha, which is the optimized function. And basically, it makes alpha an input into the model. So if you look at this diagram, you can see that the hypernetwork here in orange generates the weights data for the main network. And in this case, the main network is performing reconstruction. And so during training, we have a hyperparameter distribution, which we sample from, and we are passing those values into the hypernetwork so that it learns to generates the weights that minimizes the loss for that specific hyperparameter value. And then at test time now, instead of the distribution, we can just input any value of alpha that we want, and we would correspondingly get the reconstruction that's associated with that hyperparameter. So it opens up much more of a flexibility, twofold. One, which is that we can tune the hyperparameter now very efficiently, because inference is nothing more than doing forward passes through our model. And also, we can also view all possible solutions and choose which one is best. So instead of being stuck with a point estimate, which is the maximum likelihood estimate, now we have a whole space of different reconstructions associated with different hyperparameters. And so the end user can kind of choose which one they want to use for further downstream tasks. So especially in image reconstruction, this is a very attractive feature, because we want to give the radiologist or the clinician the opportunity to view all the different reconstructions associated with all these different hyperparameters. And in this case, the hyperparameters for image reconstruction are the regularization, the coefficients in front of the loss functions. So having a higher value alpha will change the way the reconstructions look depending on which loss functions that you use. And so this ability to give the user multiple different reconstructions, first and foremost, puts humans in the loop, So now humans have some kind of intervention within the optimization process. But also, if you want to directly tune the hyperparameter and find the one that maximizes some metric, then that's possible as well. So in the reconstruction world, we pass in a noisy image and we want the network to train the network to output the clean image, which is a unit in this case. And so what we do is the input to the hypernetwork now is going to be the alpha values, which are the regularization coefficients, and that generates the weights of the main network just as before. We experiment with two different probability distributions that we sample from during training. One, which is a uniform distribution, and another one, which we call data-driven distribution, or DHS. Uniform is very simple. We simply sample from a uniform distribution between 0 and 1 during training. But one issue with that is that we find that for certain values of the regularization coefficients, especially in the unsupervised setting, there will be reconstructions, there will be settings of the hyperparameters which give very bad reconstructions. For example, in this case, when we see beta equals 1, when beta, alpha and beta are two different hyperparameters, then you can see that the reconstructions look very bad. And we wouldn't want to ever view these reconstructions in the first place. And also, we're kind of wasting the model capacity of the hypernetwork to generate reconstructions that look like this. So that's something that's suboptimal, and we want to address that by optimizing for values of alpha that only give good reconstructions, so as not to waste model capacity. And so the way that we do that is we only optimize for alphas which have good data consistency. And data consistency is this DC, this first term in the unsupervised loss function, which basically makes sure that your measurements match your the forward model. So having a low DC will usually lend itself to having good visual structural information, which is necessary for having a good reconstruction. So the way that we approach this is that within a mini batch of B different reconstructions, we sample from alpha for uniformly, but then we only backpropagate gradients on the top K less than B reconstructions with the lowest DC loss within the mini batch. So it's kind of a stochastic thresholding mechanism where the ratio K over B is the percentage of the hyperparameter space, which is optimized. So this K is an additional hyperparameter, but we found that the results are not very sensitive for this value. Usually we chose it to be the top half of the mini batch, for example. So that would lead to optimizing for the top 50% of the hyperparameter landscape. And so here are some results. This is the hyperparameter landscape, and we see that we experiment with three different models: small, medium, and large. And this is a baseline, which is basically 100 by 100 models that we trained individually for each of these hyperparameters. And here we have single models which are able to learn the hyperparameter landscape with a single model. Okay. The top is UHS, or uniform sampling, and the bottom is data-driven hyperparameter sampling. And we can see here the histogram that shows where in the hyperparameter space we're sampling from with our data-driven sampling procedure. And lastly, here are some representative slices. So the leftmost column is the ground truth, and these two are two different reconstructions that have maximized PSNR value, but which are as diverse as possible. So you can see that from these examples, the PSNR values are very similar, but the reconstructions look very different, visually speaking. And that's kind of the power that we get from this model, is that we're now able to give the user a bunch of these different reconstructions, which are all plausible in the sense that they have high metric PSNR value. But now the user kind of has that power to choose which one they want. And it could be, future direction might be looking at specific downstream tasks which would benefit most from certain reconstructions over others. So for example, segmentation tasks may require some type of reconstruction and prefer one type of reconstruction over another. And so that would be an interesting direction for future work. This is a quantification, but in the interest of time, I'll skip it. So these are some references, and please let me know if you have any questions. Thank you.